Okay, so let's continue with the first type of microcapsule-based self-healing. This is this type of geometry where phase one, the healing material, is actually encapsulated into uh, it's encapsulated into let me just okay is encapsulated here inside a shell, and there's the catalyst that is out here. So the blue is a liquid that has a solid shell, and when the crack propagates, it goes through the material that releases it, so that then the material, the blue, becomes in contact with the catalyst, and the reaction takes place. Now, I want to use this system to explain a concept that applies equally to all types of self-healings. So the experiment they did is this: they measured fracture toughness, or based on critical energy release rate from these experiments, and there's a very easy relationship between fracture toughness and critical energy release rate, which is basically GC is Kc squared divided by the elastic modulus. Now, so basically, by measuring GC the way such as by a variation of the method I explained to you, they can measure the fracture toughness. However, if you look at this experiment, this second graph this graph that I'm showing you here, this is as a function of microcapsule concentration, which goes all the way to 25%. Now, they have two curves. One is the virgin material without healing agent. One is the healed material after the healing has taken place. So for instance, at 10%, the healing efficiency is the ratio of this guy to this guy. At 25% is at 20% is the ratio of this over that. And so basically you can easily see what happens in here. However, the concept I want to explain to you is first, let me make sure you have the question before I give you the answer. So the question I want to pose is that virgin material is a material without healing agent. So what does this, the capsule concentration, have to do with the property of the virgin material? Virgin material is the guy without capsule. So virgin material should all be here at zero concentration, but it's not. And there's a very good reason behind it. That's I give a lot of credit to PIs who did this work, who considered this. And in order to understand that, I want to go back to my, I want to go back to my whiteboard. So imagine in my big sample, this is my big sample, and this is the crack. Crack is propagating this way because there is some load that is trying to expand the material. Now, let's say I put some microcapsules there. These are empty microcapsules. Okay. So basically, keep in mind these, these guys are empty microcapsules. So basically, no healing agent. Now, if the crack propagates by some amount, and let's say initially the crack goes from here to, goes from here to here. So this is our new this is our new crack tip. Okay, so far no problem. But now let's say the crack propagates even more and it reaches this guy. Okay, so now if I zoom in this region, if I zoom in this region, what I'm going to see is something that is one of the, so what I'm going to see is that I'm going to see a crack that is like that, okay? Whereas if I zoom in here, what I am going to see is actually just a sharp crack tip. So basically, I am going to see sharp crack tip, whereas here, let me write it with blue so that we have our color code, blunt crack tip. Okay. And which one is easier to grow? Well, in this case, stress concentration around the crack tip is much, much less than this guy. Technically, technically, people would not even call this a crack tip anymore because the crack has to be sharp and there's a stress concentration there, but it's not here. So my point is the fracture toughness, or even if you consider G, C, if you don't have these microcapsules, the case where you don't have is going to be less than GC of the case where you have empty microcapsules. As a result of that, even if they're empty, okay, here we're not talking about healing. Here is the property of the material without healing. As a result of that, if I want to compare the two materials and understand the effect of healing, the two materials have to be one of them in which I have just the empty microcapsules, okay, and versus a material that now I have filled microcapsules. Okay, so basically the comparison should be this versus that. So in this case, on the left side, I have empty microcapsules, and on the right side, I have microcapsules with healing agents. And obviously, the more of these microcapsules I have, when I go from a material that doesn't have any microcapsules to a material that has a little bit of microcapsules, fracture toughness goes up because of this mechanism that I explained to you here. However, if I have too much of the microcapsules, then each microcapsule is a part of the material that is taken away. In place of these empty microcapsules, it was solid material that is now taken away. So because of these two mechanisms, either crack tip blunting or removal of the material, the fracture toughness of a material with empty microcapsules will also depend on microcapsule concentration. And so when we keep that in mind, then it allows us to go back to here and say, therefore, each concentration has to be with the same concentration. Here, the virgin material means either empty microcapsules or microcapsules that were there without healing prior to any healing has taken place. So it could be empty microcapsules here or microcapsules that have not healed yet. And so now they investigated a few things. For instance, 10% microcapsules versus 5% microcapsules versus neat. Healing efficiency of neat epoxy without any microcapsules is 0 because it doesn't heal. There's nothing to heal. 5%, you have like some good percent of healing. It's the ratio of these two. At 10%, the healing efficiency basically drops because you are pretty much you're adding these healing agents, but they're not contributing to any healing because you have certain amount of cracks, and the number of cracks per unit volume has to have a say in how much microcapsules you need to have in per volume to have the same healing. And the last graph I want to show you, so basically this is the output of an experiment like this, displacement versus load. And so initially linear, and then it breaks, or a crack starts to propagate. This, I explained the correlation between these two. And here just is the healing efficiency as a function of time. So within a few hours, you get to the healing efficiency of 50–60%. This was for just one of these cases. And then the healing efficiency doesn't change as much with time. And that's because the chemical reaction we have in mind, actually most of it happens within the first few hours. So I am gonna stop here and go to the next video.